All right, this is number 2 in what I consider the sequence of videos for week 5. Now we're going to talk just about the local density approximation. And in some sense, you've seen this to death, but we haven't really looked at the correlation piece. And so that's something we're going to focus on here just a little bit more. I can't make any physical sense or intuition out of the expression for correlation. I just can't. And so I'm not showing it to you thinking that, oh yeah, you'll get a lot of insight out of this. I'm showing it to you to say that, well, this seems to be how correlation behaves for the uniform electron gas and is the basis for the way we think about it for other systems. But the answer is, it's just complicated. And so that's really what I want you to see. So this is just a reminder of cone-sham density functional theory. I say it's LDA, it could be anything because that's really determined what EXC is. You've got a kinetic energy term from the cone-sham one, which is the sum of the individual kinetic energies of the orbitals. You've got the classical repulsion between charge densities. You've got the attraction of the electron in the nuclei. That's a really simple term, and you got an EXC. That's where all the magic is. So you can write that out with a little more detail. You can write it out as here's the cone-sham kinetic energy, here's the classical repulsion, here is the nuclear potential and the electron density, and here's EXC. And if you want to go one more, here's the sum over the orbital kinetic energies. Here's the sum, the densities written as sums of orbital densities. And so now you're going to sum over all the possible orbitals with 1/2 in front. There's the Coulomb term. There's the orbital attraction to every nucleus, and there again is EXC. When you vary that density, the functional, keeping the density, keeping the total number of particles fixed, and minimizing energy, you get something that looks like this, which determines each of the orbitals. And this is now what we call a functional derivative of the of EXC. It's how EXC changes as I change the density. And that's what determines each of the individual orbitals. And that's what gives rise then to the one electron equations. Fine. So here's EXC for LDA. We write it as basically an energy density per particle. We multiply it by the number of particles at a point. That's the density, and you integrate over all space. We break that up into 2 terms in order to make it a little more manageable, the exchange part and the correlation part. And the exchange part for uniform electron gas, we know what it is, and it is just rho to the 1/3 with some constants. That's nice and easy. Unfortunately, and I'm sorry that the picture is not better, but if you can blow it up a little bit, that will help. Unfortunately, that's not true for the correlation part. Correlation part, what we do know is 2 limits, and I'll show you them in a moment. And they are limits as a function of density. We talk about the Wigner-Seitz radius, R sub s. And when the density gets really high, you can imagine that the volume per particle, electron, gets really small. So a small RS corresponds to a big density. On the other hand, when the density is low, then each particle has a lot of space, RS gets big. You won't need that now, but I just put it out here. So here is the VWN, and this is actually VWN. There are various versions of VWN, Vasco, Valco, I can't remember the last name. But in any event, it's parameterized this way. There's a term that just depends on the 3 constants. Then there's a term that depends on the difference in alpha beta spins. And there's a term that depends on more terms like that. And each one of them has this E0, VWN, and constants in there. And the constants are different here than they are here. And here is the fundamental form of that E0 VWN. And you see, it's kind of horrific. It's the Wigner-Seitz radius. You take a log here, you got constants, inverse tangent, log, inverse tangent, square roots. And here are F1 and psi. So it's a difference in spin densities and then a function of difference in spin densities. What do you make of this? Well, you make of it, it's difficult to understand. The way this term came about was knowing what the limits were and then doing some high-level Monte Carlo calculations on a uniform electron gas to get the correlation energy at various densities, and it just fit to those. So there's no, I mean, simulations are fundamental science, but there's no paper and pencil stuff that got you this form. It's just a fit to the data. And then here are the forms. Here's how the correlation energy depends as RS goes to infinity, that is the density goes to 0. So it goes as 1 over infinity, goes to 0. And you might expect that, the electrons are so far away. And then as the density goes to 0, here's EC, and here's a function developed by Perdue and Wang that actually connects those two limits. That's their version of a functional that interpolates between low density and high density. So what takeaways do I want you to have from this? Each one of those functions, the energy densities, EC or EX, is a function of rho at a given point. It's all it depends on. ES and X is nice and simple. I wish our lives were always that way. EC, the exact, has no closed form, even for a uniform electron gas, no expression for all circumstances. VWN, as I said, fit to numerical Monte Carlo results at moderate densities and has lots of parameters and lots of forms. But, just like we said before, what the local density approximation does is it says you tell me the density at a point, I will value the exchange correlation energy density, I will multiply it by the number of particles at that point, and I'm going to integrate over all space. That's what we're going to do. That's the local density approximation. Is it good? Well, it seems to be okay for solids, not yet for molecules. And we're going to need to improve. And that brings us to generalized gradient approximations.